we were talking about arrays. Made it through about half of that, and I'm going to skip the last half of that and come back to it later because it's not required information to work your homework or to work problems on the test. So we're going to skip to the next lecture, which is 15, because there is no 14, and introduce the concepts in lecture 15. And then later we'll come back and finish the other half of the information on arrays, which has some nice to know stuff you need to understand, but not required for the test or the homework. So we want to get this business here in lecture 15 out on the table and let you have more time to ruminate on it. So we'll go straight to that information today on structures and unions. So a structure in programming language E's terminologies is a non-homogeneous composite type. Our arrays were homogeneous composite types because the thing that was repeating in the array was always the same size, and therefore we could use an index to compute an address of where it lives in memory. But with a structure, the elements of the composite are not necessarily the same size. So we see a list of types here inside of this structure that's being declared, where we have a character and an array of integers and then a double. And so you can think of that as just like an array was laid out in memory starting at some starting address and then had a repeating cell. The structure starts at some address, but the fields of the structure just sort of line up one after the other in consecutive memory locations. So this was saying if we had a character and this was address P, then at address P plus 1, you'd expect to see this integer I sub 0. You expect I sub 1 to live at these addresses, and then this double to live behind all of that stuff, right? Well, that's not exactly the way it works because we have this thing called alignment constraints on the computer. I'll explain this in a second, but the basic idea of alignment constraints is if I have a data type that requires k bytes of memory, then that needs to be stored at an address that's divisible by k. Now, exactly why we would want to constrain ourselves to doing that will become much clearer to you after we've explained how the cache hierarchy for the cache memories on the computer works and how things get moved up out of memory into those caches and ultimately into the registers at the CPU. So that'll make sense later on as to why we would have these alignment constraints. But for right now, we just assume that we have them and learn what they are. Why we have them may be clearer later. So instead of being laid out in memory just back to back to back like that, like you might think, it's actually going to be laid in memory like this. And we're going to have some pad behind that character. And the reason for that pad is to make sure that the address where this integer is laying in memory is divisible by 4 because that's a 4-byte thing. So there's 3 bytes of pad after that single byte here. And similarly, there's 4 bytes of pad after the stuff in front of it. So that this double laying in memory, which takes up 8 bytes, starts on an address that's divisible by 8. Well, to make all that work out, you'd have to take the largest alignment constraint in the list of things in your structure and make sure that the whole structure starts at an address that's divisible by that alignment constraint. So in this example, the biggest alignment constraint we have is 8 for the double. So the entire structure starts at an address divisible by 8. Then we're guaranteed that this address is starting at an address divisible by 8 because we padded it to where it's taken up 16 in front of it. So if P was divisible by 8, certainly P plus 16 is divisible by 8. So that's the reason for the pad, is so that the thing following it is guaranteed to conform to the alignment constraints for that particular type of data. 4 in the case of the integers, 8 in the case of the double. The character has no alignment constraint. It's just a byte, so it can sit anywhere, right? We'll look at this in more detail. And notice that this structure has a lot of weird syntax going on in C. And it's just like a lot of things in C, the syntax is just god awful, but you just have to learn it like everybody else. This S1 thing here is the name of a particular kind of struct that you're defining, right? Something that has these 3 fields named C, I, and V of these types. So that's the struct name. Down at the bottom, you're actually declaring a variable called P, which is a pointer to one of these struct things. So you got kind of a combination thing going on here. You got the declaration of a kind of a structure, and you got a declaration of a variable, in this case, a pointer to one of those structs. Now, what you have to realize is that in the evolution of the C language, the structs appeared first in the language before they stole the concept of declaring user-defined types with the type def that you've seen. And as a result, the structs have a separate namespace from the types that you define, which is somewhat confusing when you first start playing with C, but you have to constantly remind yourself, oh, these names like this S1 for a particular flavor of struct, I'm not using the word type on purpose, right, is a separate namespace from some type declarations or type definitions I would do with a type def, right? And there's a lot of different combinations of how those two things interact that we'll explore later. So in any event, the alignment principles are that primitive data type requires k bytes, like 2 for a short, 4 for an int, 8 for a double, that kind of thing. The address where it sits in memory has to be divisible by k, right? So it's required on some machines, like an IBM mainframe. If you don't conform to the alignment constraints, then your computations don't come up with the answers that you think they should. On the Intel machines, it's a suggestion in order to make the computer run faster and not have to be shifting things around when you're pulling them out of the cache and loading them into registers and stuff, and some other considerations that we'll see later. But anyway, you could ignore the alignment constraints on the Intel machine, but your program would run slower. So as a result, all of the compilers conform to the alignment constraints. They emit code that conforms to the alignment constraints so that your programs run fast. But there's some strangeness going on here too, because the conventions, or the set of conventions that are conformed to by those compilers, depends upon not only is it 32 or 64-bit, but also depends on which operating system this executable is targeting, which environment is it going to be executing in. And so we have a slightly different set of conventions when you're on a Windows machine from on a Linux machine. We'll point that out, what that is, in a second. So the motivation for aligning the data is to make it efficient to load or store the data up into the caches, ultimately, is what it's going to amount to. So the compiler is going to insert those gaps, those pads, into the memory image of the structs to conform to the alignment constraint. So an int has a 4-byte alignment constraint, and if it's a 32-bit machine, a pointer would have a 4-byte alignment constraint because it's a 32-bit address. A byte character doesn't have any restrictions. One byte's as good as another, right? If it's a short, the address should be divisible by 2, which would mean that the rightmost bit in the address would be a 0. If it's an int, the address should be divisible by 4, which means the rightmost 2 bits of the address would be 0. There's a little bit of variation here. If it's a double, which is an 8-byte entity, the Windows convention for code generated to run under the Windows operating system is going to have an 8-byte alignment. So the address would be divisible by 8. The rightmost 3 bits would be 0. In the Linux world, even though this is an 8-byte entity, they're only going to conform to 4-byte alignment. They just figured that it was wasteful to have those extra things, and they might incur a little bit of inefficiency from time to time, but that is the variation between the Windows and the Linux world in the 32-bit processor, is that the 8-byte alignment is done for the doubles in the Windows world, but Linux only does 4-byte alignment. This weird internal Intel 12-byte long double nonsense that we pretty much ignore in this course. Both Linux and Windows just do 4-byte alignment on that crazy thing. So when we go to the 64-bit machines, see what its alignment constraints look like. Character still a 1-byte thing, don't care where you put it. Short still 2 bytes, so you put it on a even address, something with a low order address bit of 0. The ints still, ints and floats are still 4 bytes, so they have 4-byte alignment. The rightmost 2 bits are 0 in the address. The 8-byte, and this is different from the 32-bit machine, the Windows and Linux both conform to the 8-byte alignment for the 8-byte entities, which are doubles, and now pointers are 8 bytes in the 64-bit machine, so they are on 8-byte boundaries as well. Now, a long double on the 64-bit machine is this 16-bit thing, and so those conform to 8-byte alignments, not 16. So let's look at the thing we looked at before. We got a struct, and the name of the struct, that flavor of struct, is S1. And we're declaring a pointer to one of those called P. Sitting in memory, we'd have a character, then we'd have 3 bytes of pad, then we'd have the 2 ints, then we'd have 4 bytes of pad, and then we'd have the double. The biggest alignment constraint is 8, right, under Windows x86 64. Or even a Linux on a 64-bit machine, either one, would look like this laying in memory. The beginning address of the whole struct would be divisible by 8. And then we can guarantee that if we put these pads in here, that these things will conform to the alignment constraints of 4 and 8, respectively. So you take the biggest alignment constraint you have of fields in your structure, and the whole structure has to start on something divisible by that alignment constraint, right? Then you can guarantee that the other stuff will line up properly. So now we have the 64-bit thing, right? Or Windows in the 32-bit would look like that, what we just looked at. But Linux on the 32-bit would only do a 4-byte alignment of that double. So this is what it would look like. It would start this thing out at an address divisible by 4. You'd have to have the 3 bytes to make sure that the int's laying at an address divisible by 4. But when you get over to here, since you only want 4-byte alignment, you're 12 from the beginning. So if p is divisible by 4, so is p plus 12. So it would look different laying in memory on the 32-bit machine as opposed to where it would look laid out in memory on the 64-bit machine. But Windows, even on the 32-bit machine, would lay it out like this on the top. Okay, so you take the largest alignment requirement for anything in the list, and the overall structure not only must have a beginning address that is divisible by that, but the overall length of the entire structure must be divisible by that alignment constraint. So here we've moved the double up to the front and had the character move down to the bottom, but we couldn't just chop it off here because the overall thing still has to be divisible by 8. And the reason for that is if you want to have arrays of these structures, right? Well, where the second element in the array starts needs to conform to the alignment constraint. Well, the only way to guarantee that happens is if the size of the first one took up a chunk of space such that if it conformed to the alignment constraint, so would the next one. So it has to be a multiple of the largest alignment constraint. That's why we have to have that 7 bytes on the end, even though by rearranging it like this, you don't have that 3-byte pad after the character that you had. You still don't save any bytes in this case. Sometimes you can by rearranging it like this. And that's because these guys laid out in memory all have to conform to the alignment constraints for all the fields within it. And the only way to guarantee that is that the size of that thing is divisible by the largest alignment constraint in the structure. That makes sense? Why we have to have that 7 bytes on the end. That guarantees us when we get to here that that address, if A is divisible by 8, so will this one be, because it's 24, right? So now we move to this one. And we see we've got a different struct here called S3, and we're declaring an array, a variable that is an array of 10 of these things, right? So we have to compute the offset to get to the right struct within the array, which is the, jump over the right number of elements in the array to get to the right struct. And then we have to get the offset within that struct to get to the field that we're referencing. And the way you reference a field within a struct is you use the dot to identify the field. So a sub IDX, another little silly function to show some pedantic stuff. Pass in an index, we subscript into this A thing, get to the right struct, select the J, the field named J within that, which means you got to have an offset that gets you down to where that is in the struct. So the length of all that stuff in front of it. Well, where is that? How's it laid out in memory? Well, it's got the I. This alignment constraint on this is 4 is the biggest alignment constraint, the float. So this has to start on an address divisible by 4. That I took up 2 bytes. The V needs to start on an address divisible by 4, so we had to put 2 bytes of pad in there to guarantee that. And then you have your J, which is your short, and then we got 2 bytes of pad because the overall length of the thing has to be divisible by 4. So these things are of what length are these structs, right? What are they? Well, this is 2, 4, 8, 10, 12. So these things are 12 big, right? So to jump over them to get to the right one in the array, we'd have to jump over 12 bytes times the index and add it to where the whole array started at A, right? To get to the right struct, and then to get to the right field within the struct, we'd have to add an offset. To get to J, we'd have to add an offset of 2, 4, 8, right? So address of A, the beginning address of the whole array, plus 12 times the index plus 8 gets you to the J field within struct A sub I. So we look at the addressing modes, and we've got an addressing mode that's perfect for that, right? Remember our addressing mode for playing with arrays? So this one is saying, okay, I want to multiply IDX times 3. So we do the little cheating trick of shift it left a bit and add it to itself. So we get 3 times the index. And now we're going to say multiply that times 4, which gets you to 12 times the index, right? And they're showing this as the beginning address of the array plus 8 to get to the J field. Well, in reality, what would probably happen is this beginning address of the array would be sitting in this position here, in your 3-part addressing form. So that would give you 4 times that added to the beginning address of the array, and then you go 8 past that, right? So that would give you the address of the J field within the ith structure. We have a question. Does this mean that structs will have different sizes depending on the order in which we define their parts, or will the compiler typically optimize the order for us? This is a systems programming language where we're going to be going into memory and doing pointer arithmetic and need to know exactly how things are laid out in memory, right? So C is not allowed to rearrange these things from the way that we listed them, because we need to know exactly where they lay in memory. If we start doing pointer arithmetic and moving around to grab the fields, we need to know how they're laid out. So in C, it is never the case that it puts them in memory any differently from the order in which you listed them there. Compiler is not allowed to do that. In other languages where you have no concept of an address, like Java strictly outlaws the whole concept of an address because you're not really dealing with the real computer in the first place, right? You're dealing with a make-believe thing implemented by executing little make-believe byte codes rather than the actual instructions on the computer. That's what it's compiling to, a little stack machine. So in that kind of language, there is no direct relationship between you, the programmer, and how things lay in the memory of the computer. So in that kind of language, it could be free to move things around if it wanted to. But in a systems programming language where we're talking about pushing things right down onto the actual bare metal, the memory of the computer, directly manipulating it, it can't change the order. It has to do it exactly like we told it to do, so we know exactly where they're laying in memory. You can manually yourself try to rearrange the fields in order to minimize the amount of pad. And we'll look at that in a second. Sometimes you can, sometimes it doesn't work. So if you wanted to minimize the amount of pad that was needed to conform to the alignment constraints, the heuristic would be, well, move the biggest ones up to the front, right? Take your very biggest thing, in this case, an int, it's bigger than the 2 chars, and move it right up to the front. If you had the C first, you'd have to have 3 bytes to make sure this integer lived at a divisible by 4 address, right? And then you'd have this other character hanging off the end, and the overall length of the sucker has to be divisible by 4. So you got 6 bytes total of pad. If you put the integer first, the big guy, he's going to start the struct on something that's divisible by 4. We don't care where these bytes go. They don't have any alignment constraint. The overall thing needs to be divisible by 4, so I only need 2 bytes to make that happen. So I saved myself 4 bytes, right, by rearranging the order. but I have to manually do that. The compiler can't just do that for me because if I listed it like this, I need to know exactly where they're at in memory, that they will be in those locations. Okay. Systems programming. We're directly manipulating the memory of the computer, the real actual computer, not a make-believe computer. Okay. So now we get to this concept of unions. And a union kind of looks like a struct, got the name union instead of struct, and then you can give that union some name, that flavor of union. I don't use the word type because it's a separate namespace from the types, right? And then I list the fields that I want in the union, and here I'm declaring a pointer to one of these union guys. But unlike the struct, rather than laying the fields that I list like this, the same field descriptions in my struct S1, rather than laying them out in memory back to back, the union is simply a redefinition or a redescription of the same hunk of memory. So I take the biggest thing that's in there, this double, and this union will take up that much space, these 8 bytes. These other things are just redescriptions of that same 8 bytes in memory. So if I reference the field name C in here, I'm just picking up this first byte here. If I reference I sub 0, I'm referencing the first 4 bytes. If I reference I sub 1, I'm referencing the second 4 bytes. V, the double, refers to the whole 8 bytes. So it's just a way of redescribing memory in however many different ways I wish to look at it. Well, as soon as you allow that to happen without having what's called a discriminant associated with the union that tells you what's sitting in there currently in memory, you've totally lost all ability for the language to be what we call strongly typed. So C has no pretenses of ever being anywhere near in the same state with a language called a strongly typed language. You can get around the typing system 17 different ways, and here's one of them, right? So you're just saying, stuff these bits in there for a double. Oh, now pick the first half of that double up and pretend it was an integer. Well, we know that the encoding format for these floating point double things is a completely different beast from the integer encoding format. And we're just picking up whatever the heck those bits are at the front and pretending it describes an integer. So that just blew any kind of typing off the planet, right? You stuffed it in one way and you pulled it out as if it was another, right? It isn't changing the bits like you would do if you cast an int to a double or a double to an int, right? It's just picking up whatever bits are laying there in those memory locations and us interpreting like they were the other type, right? So strong typing just went completely out the window. Different languages have different sort of approaches to this concept. Some languages require you to have a thing called a discriminant, and the discriminant always tells you what flavor of thing is actually living in there. And if we have time, I'll show you some examples from some other languages that deal with this issue in a different way and can retain strong typing while still having these unions. So anyway, unions are not the same thing as structs. They look a lot like structs, but rather than a sequence of things laid out in memory, it's just a redescription of some chunk of memory. They also live in a separate namespace from the types, right? So now we get it confusing because we have a type definition, and what we're defining, the name of the type we're creating is called bit float type, right? This convention of putting a T at the end of the name of the thing is a convention that is used in all of the C libraries. When you have a type defined in those libraries, the name will always have that underbar T on it telling you that that's the name of a type. And so here they're just conforming to that same sort of convention for how they named the type we're creating, bit float type. And it is a union of these things. What's the biggest thing in there? Well, they're both 4, so this whole union takes up 4 bytes, but I can refer to it as an unsigned, or I can refer to it as a float, the same 4 bytes, right? Now we have a little silly pedantic function called bit to float, and you pass it in an unsigned and it returns a float. Well, what does it do? It takes the unsigned and it declares this arg variable be one of these bit float type guys. And then we say, take that unsigned and stuff it into the U field, which is an unsigned, in my variable arg. And now I want to pick up that same 4 bits and I want to shove it out by picking up the float field, the F field, return that as the float. So the bits came in as an unsigned. I stuffed it in there and then I gave it back to you as if it was a float. The bits didn't change. So that's not the same as casting the unsigned to a float, because if you cast the unsigned to the float, it'll concoct a floating point representation that represents that same number, right? And you've seen how that's totally different from the way these integers look, right? But here we're not changing the bits. We're just saying, oh, I want to pretend it's one of these types instead of one of those other types, right? For whatever devious reason you might want to do that. And then to go the other way, you could pass it in as a float, stuff it in there, and then pull it out as an unsigned and return that back, right? So you have ability to do some very dangerous things that may be completely meaningless, right? Unless you know what you're doing. So we understand unions, hopefully, right? So now we get back to the byte ordering issue. Shorts, longs, quad words stored in memory as either 2, 4, 8 consecutive bytes. Which is the most or least significant? Well, that depends on whether it's big Indian. When we have a numeric value, right, it matters whether the computer is using little Indian or big Indian for how that actually stored in memory. So if we had this union of these 4 fields that we're describing, it's 8 bytes of memory redescribed 4 different ways, right? 4 characters, 8 characters, 4 shorts, 2 ints, or 1 long. On the 32-bit machine, remember the long is a lie. It's the same size as an int, so it's really only the same first 4 bytes there, right? And we're declaring a variable called DW, which is one of this flavor of union, right? If it was the 64-bit machine, the long is actually a 16 is an 8 byte entity now rather than a 4 byte entity, right? So it would be referring to this whole chunk of 8 bytes, right? So now what about little Indian, big Indian stuff? Well, if we have our for loop, we're going to walk through the DW as our variable name, and then we're selecting the field C, right? C is this array. That's the name of the field, right? And you select it by saying DW dot the name of the field. Oh, that thing is an array, so I subscript it. So you get the 0th element and you put F0 plus 0, and then you go 1, and you put F1, right, into slot 1, you put F2 into slot 2, etc. So we lay those values in the memory in those bytes, right? And then we want to print it out 4 different ways. So we're going to print it all of it in hex, print out all the characters for the 8 bytes, pretending they're characters. Now printed as if they're 4 shorts. Now printed as if they're 2 ints. Now printed as if it's a long. So what are we going to get? On the 32-bit machine, if it was a little Indian machine, like the Intel processor is, then F0, F1, F2 is laying in those 8 bytes that we stuffed in the for loop, right? You pick it up as characters, you just see the F0, F1, you know, the hex, right? But you pick it up as a short, what are we going to see? Well, it's a little Indian machine. So the least significant byte is at the low address, and the most significant byte is at the high address. So that looks like the number F0. I mean, F1, F0, right? This looks like the number F3, F2. If you pick up this int, then this is the most significant byte. So you're going to see F3, F2, F1, F0. It's a little Indian computer. And the long, you get the same thing as that. Everybody okay with that? So little Indian, big Indian rears its head again, right? If it's a big Indian machine and you pick up that short, well, the most significant byte is at the low address. So there it looks like the number F0, F1 as far as it's concerned, right? You pick up this int, this is the most significant byte, so it looks like that number as an int. That makes sense? So little Indian, big Indian, once again, matters. If it's the 64-bit machine, like Intel 64-bit machine, little Indian, it would look like this stuff, right? You pick up the F1, F0, the F3, F2, F5, F4, F7, F6, right? For the shorts. For the ints, you pick up F3210 as what the number is, right? Little Indian computer, least significant byte at the lowest address. But you pick up the long on the 64-bit machine, unlike on the 32-bit machine, you get the whole sucker because it's 8 bytes, right? So it looks like that number, not this number that you would have got if it was the 32-bit machine. Questions about that? So to summarize, we looked at arrays, which are homogeneous composite entities, right? Contiguously allocated in memory, aligned to satisfy every element's alignment requirement. We didn't really talk much about that or at all when we were talking about arrays, but the beginning of the array has to be on a boundary, an address that conforms to the alignment constraint of whatever the cell size is of the array. So if you had an array of integers that started, the whole array would start on an address divisible by 4, right? If it was a 64-bit machine and you had an array of longs, the array would have to start on an address divisible by 8. And that's because then each element within the array would conform to the alignment constraints, right? Structures allocate bytes in the order declared, pad in the middle and the end to satisfy all the alignment constraints. Unions just overlay the same chunk of memory with different descriptions, right? And it's an easy way to circumvent the typing system. Think back to your is little Indian, big Indian program you had to write for the first homework assignment. Well, you could have used a union to describe the thing as an int and as characters, right? And then went in and picked up the character to see whether it was little Indian or big Indian, right? That would have been another way to solve that problem. But you didn't know about unions back then. Okay, does that make sense? Questions about structures and unions. So the syntax of this stuff in C is just horrible, but that's the way it is, and you're just going to have to deal with it. There's a lot of combinations of ways you can describe this nonsense. Let me show you a few. Here we're declaring a struct, and we're giving that struct a name, right? And we say it has these fields of those types. Then, if I want to declare a variable of one of those structs, I would say struct. I'd have to use the word struct and then the name of the struct, and then I could declare a variable to be one of those guys. The other way you could get there is you could say struct, the name of this struct is an S2 flavor of struct. It has these fields, and then right at the bottom, in the combination sort of way of doing it, you go ahead and declare a variable to be one of those guys. If you wanted some more variables to be of this flavor of struct2, then you could do like that, struct S2 variable name or whatever, right? But you also have types in C, which are separate from the names of the structs. So I could say type def, and what am I defining? I'm defining a type called struct type, right? And what is it? Oh, it's one of these S1 structs. So now I can declare variables to be of type struct type, and you would do that like this by putting the type name and then the variable, but notice you don't use the word struct. You only use the word struct when you're declaring it from the name of a struct, not the name of a type. So you see these little slippery differences between the world of types and the world of struct names, right? So you could have, like they showed you in the book, a big combination of all of this nonsense where you say type def struct S1, and then you'd have the whole definition of what the struct looks like laying in there. And then you could declare a variable. Uh, the name of the type def would come down at the bottom then. You know, that flavor, I'll just write it out for you. I'll use a struct S2 thing or something. Let me see. Type def, and now I'll call it S3 or something, struct. And in this case, I can put a name for the struct, or I can just leave it off if I want, right? And then I would just list the fields for the that are in the struct, right? Like, you know, char, zip, int, dig, whatever, right? And then down at the bottom here is where I put the name of the type. Something type, right? So you got all these different sort of combination ways of how you can describe this, and it can be somewhat confusing when you first start messing with it, right? But the thing is to remember that the names of the structs aren't types, right? You get names for types by using type def. But the thing you're creating the type for could be a struct. You could have a name or not have a name, right? Here I said type def struct S1 struct type, right? So now I have a type called struct type, and every time I declare something, one of those, I get a variable that's one of these S1 structs. Does that make any sense at all? So the syntax is a result of the fact that structs existed in the language before they introduced this concept of type defs. They stole type defs from the concept of a type, a user defined type in the Pascal language. They did that after they stole structs from Algol. Okay, so it's a little confusing, right? So if you have, you could say struct type, and I've declared that to be a type, right? So now I can use it as a type name, comes first before the variable name in a declaration, right? And now I'm declaring an array of 10 of those struct types, but the struct type is a S1 flavor of struct. So each element of the array has these three fields, right? And so you see a for loop assigning into a sub I to select which element of the array I want, right? And then I'm selecting the field I, which is a different use of the name I. Does everybody see that? This I is the I variable of the for loop being used as the index in the array, but dot I refers to the name of the field that I gave it in the struct. No, you could use a type inside a struct that had been created in another type def, but you couldn't put a type def itself inside the struct. I could say, I have this type called struct type, right? And I could do something like this if you wanted to type within there. This is slower than Christmas. So I could do some crazy thing like this. Since I have this name called struct type, I could now declare a struct S4 flavor of struct, right? And it has some fields in it. And I could come in here and say, oh, I want a field. And the type of this field is struct type. And it's called S. And the type of this field is jar or something. And it's called CX or something, right? So this is a type like any other type. So I can declare a field to be of that type inside the struct, but I couldn't just use the word type def here inside the struct. Okay, so this can be confusing as hell, right? When you first start learning how to write C. I mean, I try to warn you every time I can. The syntax in C is horrible. It sucks. It's just god awful bad. So what did they do when they invented the language Java? What did they steal from C? It's syntax. The rest of it has nothing to do with C, but they stole this god awful syntax. It just makes no sense whatsoever. So, anyways, there's a lot of things in this world that, you know, are not going to add up and make sense ultimately. It's just the way they are, right? And the syntax of C is just this product of evolution, and it's just horrible, but you have to learn how to read it and write it. So hopefully this points out some of the pitfalls. Notice the one here. Make sure you understand that I is a variable here, and this I is the name of a field within a struct that's being selected, right? Right. So it's just pretty ugly stuff. Well, you need to know this stuff to work your second homework problem. So that's why I moved it to today, so you have more time to ruminate on it. And this stuff is on the test, so you need, let it sink in a little. So tomorrow we will look at, well, when I compile this nonsense, what does the assembly language look like for accessing all of these fields in the struct? And then if we have any time left over, we'll go back and finish off that second half of lecture 13 about some other sort of fun to know things about arrays and passing them in as parameters to functions and how all that works. So any questions about anything before we close it up for the day? Office hours are at 1 on Wednesdays, right? I think I lied to the previous class this morning. I told them 2. But office hours are at 1:00 on Wednesdays because I have a research meeting at 2. So anyways, maybe I see you at office hours, maybe I see you tomorrow for class. And that's our last class before, well, we actually do have a class Friday. So depending on when you take the test, you may or may not have that one before the test. So anyways, hopefully this stuff makes sense. Any questions? Okay, well then we'll wrap it up and see you tomorrow or at office hours at 1. Have a good one. Adios.